Deployments describe a desired state of pods. For example, a desired state could be that you want to make sure that you have 5 Nginx pods running at all times. Its declarative stance means that Kubernetes will continuously make sure this configuration is running across your cluster. Kubernetes also supports various update mechanisms for deployments, which I'll tell you about later in this module. Deployments declare the state of pods. Every time you update the specification of the pods, for example, updating them to a newer container image, a new replica set is created that matches the altered version of the deployment. This is how deployments roll out updated pods in a controlled manner. Old pods are removed from the old replica set and replaced with newer pods in a new replica set. If the updated pods are not stable, the administrator can roll back the pods to a previous deployment revision. You can scale pods manually by modifying the deployment configuration. You can also configure the deployment to manage the workload automatically. Deployments are designed for stateless applications. Stateless applications don't store data or application state to a cluster or to persistent storage. A typical example of a stateless application is a web frontend. Some backend owns the problem of making sure the data gets stored durably, and you'll use Kubernetes objects, other than deployments, to manage these backends. The desired state is described in a deployment YAML file containing the characteristics of the pods coupled with how to operationally run these pods and their lifecycle events. After you submit this file to the Kubernetes control plane, it creates a deployment controller, which is responsible for converting the desired state into reality and keeping that desired state over time. Remember what a controller is. It's a loop process created by Kubernetes that takes care of the routine tasks to ensure the desired state of an object or set of objects running on the cluster matches the observed state. During this process, a replica set is created. A replica set is a controller that ensures that a certain number of pod replicas are running at any given time. The deployment is a high-level controller for a pod that declares its state. The deployment configures a replica set controller to instantiate and maintain a specific version of the pods specified in the deployment. Here is a simple example of a deployment object file in YAML format. The deployment named my-app is created with 3 replicated pods. In the spec.template section, a pod template defines the metadata and specification for each of the pods in this replica set. In the pod specification, an image is pulled from the Google Container Registry, and port 8080 is exposed to send and accept traffic for the container. Any deployment has 3 different lifecycle states. The deployment's progressing state indicates that a task has been performed. What tasks? Creating a new replica set, or scaling up, or scaling down a replica set. The deployment's complete state indicates that all new replicas have been updated to the latest version and are available, and no old replicas are running. Finally, the failed state occurs when the creation of a new replica set could not be completed. Why might this happen? Maybe Kubernetes couldn't pull the images for the new pods. Or maybe there wasn't enough of some resource quota to complete the operation. Or maybe the user who launched the operation lacks permissions. When you apply many small fixes across many rollouts, that translates to a large number of revisions and to management complexity. You have to remember which small fix was applied to which rollout, which can make it challenging to figure out which revision to roll back when issues arise. Remember earlier in the specialization, we recommended that you keep your YAML files in a source code repository. That can help manage some of this complexity.